Elixir, agent. In this chapter, we will create a module named kv.bucket. This module will be responsible for storing our key value entries in a way that allows them to be read and modified by other processes. If you have skipped the Getting Started guide or read it along the way, be sure to reread the Processes chapter. We'll use it as a starting point. The trouble with state. Elixir is an immutable language where nothing is shared by default. If we want to provide buckets, which can be read and modified from multiple places, we have two main options in Elixir: processes and ETS, Erlang Term Storage. We covered processes in Getting Started guide. ETS is a new topic which we'll explore in later chapters. When it comes to processes, though, we rarely hand roll our own. Instead, we use the abstractions available in Elixir and OTP. Agent. Simple wrappers around state. GenServer. Generic servers, processes, that encapsulate state, provide sync and async calls, support code reloading, and more. Task. Asynchronous units of computation that allow spawning a process and potentially retrieving its result at a later time. We will explore most of these abstractions in this guide. Keep in mind that they are all implemented as on top of processes using the basic features provided by the VM, like send, receive, spawn, and link. Agents. Agents are simple wrappers around state. If all you want from a process is to keep state, agents are a great fit. Let's start an IEX session inside the project with IEX S mix and play a bit with agents. So agent.startLink, some function, end. Agent.update, agent, make a new state of change the state that this has updated. Existing state, new state. Agent.get, agent, and then which is going to return get agent, and then run some function on its state. And here, this makes it return the list or the state of that agent, which in this case is a grocery list. Agent.stop, agent. Okay. We started an agent with an initial state of an empty list. We updated the agent state, adding our new item to the head of our list. The second argument of agent.update3 is a function that takes the agent's current state as input and returns its desired new state. Finally, we've retrieved the whole list. The second argument of agent.get3 is a function that takes the state as input and returns the value that agent.get3 itself will return. Once we are done with the agent, we can call agent.stop3 to terminate the agent process. Man, I was thinking about asking Elnicky for a Elixir book recommendation during that paragraph, so we're going to reread it. We started an agent with an initial state of an empty list. Here. We updated the agent state, adding our new item, eggs, to the head of the list. The second argument of agent.update3 is a function that takes the agent's current state as input and returns its desired new state. Finally, we retrieve the whole list. The second argument of agent.get is a function that takes the state as input and returns the value that agent.get3 itself will return. The second argument of agent.get, this function, is a function that takes the state as input and returns the value that agent.get itself will return. So it's just like, hey, I wanted to get the third item in the list. You return an at and then list, comma 2, right? Once we are done with the agent, we can call agent.stop to terminate the agent process. Let's implement our KV bucket using agents. But before starting the implementation, let's write some tests. Let's drink some water. Create a file at test kv test or bucket test.exs. Remember the .exs extension with the following. Def module kv.bucketTest do use xunit case async true test stores values by key kv.bucket.startLink. See the bucket or the agent. And agents are lightweight wrappers around state. Cool. Assert the kv bucket get bucket milk, which is going to be the key, is nil. kv.bucket put bucket milk 3, and then assert that it is it's at that location. Our first test starts a new kv bucket by calling the startLink 1 and passing an empty list of options. Then we perform some get2 and put3 operations on it, asserting the result. Also note the async true option passed to xunit case. This option makes the test case run in parallel with other async test cases by using multiple cores in our machine. This is extremely useful to speed up our test suite. However, async must only be set if test case does not rely on or change any global values. For example, if the test requires writing to the file system or access a database, keep it synchronous. Omit the async option to avoid race conditions between tests. Async or not, our new test should obviously fail, as none of the functionality is implemented in the module being tested. In order to fix the failing test, let's create a file at lib kvbucket.ax with the contents below. Feel free to give a try at implementing the KV bucket module yourself using agents before peeking at the implementation below. So startLink, we're essentially delegating to agent and providing it an initial state here. Get a value from the bucket by key. Use agent. The bucket must be equal to return value of this, or the first in that tuple. Get bucket key, agent.get bucket, and then map.get the state of the bucket, the state of the agent, and the key. And put, similar but with map.put and key value. The first step is our implementation. In our implementation is to call useAgent. Then we define a startLink function, which will effectively start the agent. It is a convention to define a startLink1 function that always accepts a list of options. We don't plan on using any option right now, but we might later on. We then proceed to call agent.startLink1, which receives an anonymous function that returns the agent's initial state. We are keeping a map inside the agent to store our keys and values. Getting and putting values on the map is done with the agent API and the capture operator ampersand, introduced in the Getting Started guide. Now the KV bucket module has been defined, our test should pass. You can try it by running mix.test. Test set up with xunit callbacks. Before moving on and adding more features to kv.bucket, let's talk about xunit callbacks. As you may expect, all kv bucket tests will require a bucket agent to be up and running. Luckily, xunit supports callbacks that allow us to skip such repetitive tasks. Let's rewrite the test case to use callbacks. So now we have this setup macro, setup macro that runs the bit of code that you want to set up, and it returns something that you can then grab in your tests. We have first defined a setup callback with the help of the setup1 macro. The setup1 callback runs before every test in the same process as the test itself. Note that we need a mechanism to pass the bucket PID from the callback to the test. We do so by using the test context. When we return bucket from the callback, xunit will merge this map into the test context. Use the test context. Since the test context is a map itself, we can pattern match the bucket out of it, providing access to the bucket inside the test. Wonder what else is available in the test context. Other agent actions. Besides getting a value and updating the agent state, agents allow us to get a value and update the agent state in a function call via agent.getAndUpdate. Let's implement a kv.bucket.delete2 function that deletes a key from the bucket, returning its current value. Delete map.pop at the key. And client/server in agents. Before we move on to the next chapter, let's discuss the client-server dichotomy in agents. Let's expand the delete2 function we have just implemented. Delete bucket key, agent get and update bucket, and then the state. Just expanded a bit. Everything that is inside the function we passed to the agent happens in the agent process. In this case, since the agent process is the one receiving and responding to our messages, we say the agent process is the server. In this case, since the agent process is the one receiving and responding to our messages, we say the agent process is the server. Everything outside the function is happening in the client. This distinction is important. If there are expensive actions to be done, you must consider if it will be better to perform these actions on the client or on the server. For example, say we sleep for a second, and we're adding a couple seconds of sleep. When a long action is performed on the server, all other requests to that particular server will wait until the action is done, which may cause some clients to time out. In the next chapter, we will explore gen servers, where the segregation between clients and servers is made more apparent. All right, neat. We'll be back